All right, so this problem says two charges, Q1, 2 microcoulombs, and Q2, 2 microcoulombs. Okay, are placed symmetrically along the x-axis at x equal to plus and minus 3 centimeters. Okay. Consider a charge Q3, 4 microcoulombs, and mass 10 milligrams moving along the y-axis. If Q3 starts from rest at y equal to 2 centimeters, what is its speed when it reaches 4 centimeters? Okay, so let's draw this. Okay, Q1 and Q2 are at 3 centimeters. All right, so this charge moves from 2 centimeters to 4 centimeters. Again, you want to find the speed of this charge at this point. It's starting off at rest. Okay. All right, so this is an energy conservation problem. So this is the initial configuration, and this will be the final configuration. The potential energy in the initial configuration plus kinetic energy in the initial configuration equal to potential energy plus kinetic energy in the final configuration. Kinetic energy is 0. These charges are fixed, and this is the only guy that can move. So we are talking about the energy of the entire system. The kinetic energy is 0, and at this point it's moving, so this will be non-zero. So what is happening is the potential energy of this system in the initial configuration will be larger than the potential energy of the system in the final configuration. And so the potential energy is being converted to kinetic energy. Just like this object, when you drop this object, okay, its potential energy is decreasing, and that's what's being converted to kinetic energy. All right, so we'll call this R initial. Okay. And notice the two distances are the same, and this is R final. Okay. So let's calculate those distances first. R initial is equal to square root of 3 square plus 2 square, 9 square root of 13 centimeters. R final is 3 square plus 4 square, so 5 centimeters. Okay. All right, so potential energy initial is the formula for the potential energy. So potential energy initial, all right. K Q1 Q3 divided by R initial plus K Q2 Q3 divided by R initial. And Q1 and Q2 are the same. So this is 2K Q1 Q3 divided by R. Yeah. So let's put in these values. K is 9 times 10 to the 9. Q1 and Q3 are 2 and 4 microcoulombs. I've combined the two. So Q1, Q2 is All right, maybe I'll. And our initial is square root of 13 into 10 minus 2 meters. Okay. So let's look at the potential energy initial. That's 10 minus 12. You get 10 minus 3. And then 10 minus 2 gets killed here, so you get 10 minus 1. So this is, and 2 times 9 is 18 into 8 divided by root 13. And this is potential energy, so this will work out to be joules, that many joules. Four joules. Okay, so we'll do potential energy final. Again, K, Q1, Q3, R final, Q2, Q3, R final, equal to 2K, Q1, Q3, because Q1 and Q2 are equal, R final. Okay, everything is the same except for root 13 gets replaced by 5. Our final is 5 centimeters. So the simple trick is multiply this by root 13 and divide by 5. Okay? So we'll multiply 4 by root 13 and divide by 5. So 2.88 joules. Okay. All right. So now we have this piece and we have this piece. So now we can calculate the kinetic energy. Okay. So kinetic energy is P E initial minus P E final equal to 4 minus 2.88 joules, and that's equal to 1/2 mv squared. And the mass was 10 milligrams. Yeah, the mass of this is 10 milligrams. 10 milligrams, that's 10 minus 3 grams, and a gram is 1 milligram is 10 minus 3 grams, and a gram is 10 minus 6 minus 3 kgs. So into 10 minus 6 kgs. Okay. All right, so if you bring this to the top, that becomes 10 to the 6. Square root of that is 10 to the 3. So we get 10 to the 3, and this is meters per second, divided by 2.24 divided by 10, square root of that. And 10 to the power of 3 meters per second is a kilometer per second. Okay. So, and this works out to 473 meters per second. So it's going at 500 meters per second, roughly from here to Mainland High School. Okay. So the electrostatic force is quite strong. A charge like this in 2 centimeters accelerated from 0 to 500 meters per second. Okay. Okay, this problem says, what is the average power output of a heart defibrillator that dissipates 400 joules of energy in 10 milliseconds? Okay, so a defibrillator is sometimes your heart goes into chaotic beating, and if you don't get a regular beat going, it can be fatal within a few minutes. Okay. And so all you do is pass a current through your chest wall, and it goes back to regular beating. Okay, so you're going to dissipate 400 joules of energy in 10 milliseconds. Okay, so the power is energy divided by time. (40 into 10 to the 3 watts). Okay, so 40,000 watts. When they give you that shock, the power rating is 40,000 watts. So the question is, why don't you burn your heart or your chest cavity? Yep. Any ideas? What's that?
They have pads that
No. So it's total energy is what matters. Okay, so for instance, I'm trying to think of an example. If you take a match and light it, I mean, when it burns slowly, it doesn't hurt that much. You can make that match release all its energy very fast, and you'll have a loud explosion, but it won't bring down a building. Okay, it's the total energy that matters. Okay, so let's say we dump this much energy into your body. Let's say 100 grams of the body. We'll just say 100 grams. Let's see if it will burn you. Your body essentially is water, so that's the specific heat of water. All right, so let's see what will be the temperature rise when you dump that much heat. Yep. 400 joules, and mass is 0.1 kg. And specific heat of water is 4,186 joules per kg per degree Celsius. Okay, so okay. I guess I should take more than 100 grams, but even in this worst case scenario. Okay, so in that locality, the temperature will rise by 0.96 degrees Celsius. If you dumped all that energy into 100 grams, which is that much, well, a little more than that much. Okay. So if it were a kg, if this were 1 kg in 2.2 pounds of your chest, then that would be 1/10 of a degree. Okay. So That's not a whole bunch of energy. Yeah. This problem says an evacuated tube uses an accelerating voltage of 40 kilovolts, 40,000 volts, to accelerate electrons to hit a copper plate and produce X-rays. Do you guys know how X-rays are produced? So what you do is you take a wire, heat it, and it'll spit out electrons, and then it'll spit out electrons, and then so in this machine we are applying 40,000 volts. Okay, and the electrons will accelerate towards the positive plate. Okay, so they'll be going quite fast, and then you make them hit this wall, and they will lose all their energy, I guess, and emit X-rays. Okay, so they'll get stopped, and they'll emit X-rays. All right, so you saw that what happens is when an electron falls through 1 volt, what is its energy? 1 electron volt. Okay, so it falls through. The energy of the electron when it fell through 40,000 volts is 40,000 electron volts. Okay, and that's equal to what would be the speed of this electron? So we're calculating the speed of this electron just before it hits the wall. Okay? So, and that's equal to 1/2 mv squared. All right, so, and 1 electron volt, we will convert that to joules, and the conversion factor is 1.6 times 10 to the minus 19 joules. So, okay, so V is 2 times E divided by the mass of the electron, square root of that. Okay, so let's put in these values. 2 times E is electron volts, and so there's the electron volts to joules conversion, and the mass of the electron is 9.11 times 10 to the minus 31 kg. Yeah. All right, so again, you want to take care of powers of 10 first. Bring that to the top, you get 10 to the 12, square root of that, okay, 10 to the 12, 10 to the 15, 10 to the 16. Square root of that is 10 to the 8. And then the rest of it is 2 times 4 is 8, 8 times 1.6 divided by 9.11. All right. That's the velocity of the electron just before it hits the wall. Do you guys know what is the velocity of, what is the speed of light? I'm sorry? 3 times 10 to the 8 meters per second. Okay, so this is 33% the speed of light. So at these speeds, you can't use this formula for the kinetic energy, but we are doing an approximation and using it. Okay? So the correct formula for the kinetic energy at those speeds would be something called gamma 1/2 mv square, and gamma is 1 over square root of this thing is messy. This might work out to a factor of 2 or something, but it's messy, and we're going to be lazy and we're not going to do it. But you've also not seen it before. Yeah. All right. You have to do relativity for that. Become friends with Einstein. Yeah. All right, so this problem says, find the maximum potential difference between two parallel conducting plates separated by 1/2 centimeter. 1/2 centimeter is that much? Okay. Of air, given that the maximum sustainable electric field strength is in air is 3 times 10 to the 6 volt per meter. What does this mean? The maximum sustainable electric field strength is that?
Before it has electricity.
I'm sorry?
Before there's thunder or like lightning.
All right, so if the electric field gets stronger than that, you'll have, it'll short. Air will become conducting, and any energy stored in the capacitor will be discharged. Okay. So here are two parallel conducting plates. The distance between the plates is 0.5 centimeters. And there's the electric field. Okay. The voltage between the plates when the electric field is constant is E times D. So V max, the maximum voltage you can charge this capacitor to, is E max times D. Okay. So the maximum potential difference is E max you can have is 3 times 10 to the 6 volts per meter. And D is 1/2 centimeters, 0.5 into 10 minus 2 meters. That's 1.5 into 10 to the power 4 volts. In the next chapter, you'll see that in a capacitor you can store energy, and the higher the voltage you can charge it to, the more energy you can store. Okay? So you would like to store as much energy as possible, but there's always a limit to the amount of energy you can store before it'll discharge and all your energy will leak away. Okay? Okay, so in this problem says the electric field in a region is pointed away from the z-axis. So there's a z-axis. The electric field is pointing away from the z-axis. So the electric field is pointing away like that. The magnitude of the electric field is given by that. Alpha constant divided by S. S is this radial distance. As alpha over S, where alpha is a constant. Find the potential difference between point P1 and P2. Okay. So if you check your notes, V2 potential at point 2 minus potential at point 1 is negative of E dot ds from the initial to final point. Okay, it's this line integral, and we're going to do this line integral. Okay. All right, the line integral is, it'll turn out to, well, it's path independent. So you can choose any path. So what we'll do is we'll choose this path. We'll go along like this and then like that. Okay. Okay, so along this path, you see ds is like this. So ds is like that, and e is like that. E is perpendicular to ds. This is 0. So the value of the line integral along this path is 0. And then so the only non-vanishing part is this part. Okay. And along this path, E and ds are parallel to each other. Okay. So this is equal to minus, we'll call this P1 prime to P2 E dot ds. So V2 minus V1 equal to minus, and P1 prime, so S is the radial distance, is A to B, E is alpha over S ds, minus alpha log S B2. All right, so what is this formula saying? The potential at point 2 minus the potential at point 1 is negative. Alpha is a positive constant. This is positive. Okay. B over A, that's greater than 1. This is positive. Okay. So, and you know that the electric field points in the direction of decreasing potential. So potential at this point is greater than the potential at this point. Okay. What hopefully you've realized is these are equipotential surfaces. Okay. And that's the potential difference between the 2 points. Okay. All right, this problem will show you how much energy there is in, nuclear energy is, how much more energy there is in when you split a nuclei. Yeah. In nuclear fission, a nucleus splits roughly in half. Okay. So generally in nuclear fission, what you do is you take uranium, and you take the uranium-235 isotope in most nuclear reactors. You shoot it with an electron and with a neutron, and the neutron has to be a slow neutron going at about 2 kilometers a second. Okay, so a neutron that is going from here to the speedway in 1 second. So you shoot a neutron like that. This neutron gets absorbed. This starts shaking, it vibrates, and then breaks up into 2 equal pieces. And then it's, on the average, spits out 3 more neutrons. Okay. All right, so these are the ingredients, this is the product. Okay. This is the mass of the ingredient, this is the mass of the product, and the mass of the product is less than the mass of the ingredients. Why is the mass of these guys less?
Energy got released. The mass got converted to energy.
Yeah, but why is the mass less? And the missing mass is what got converted to energy, so you skipped a step. My question is, the missing mass got converted to energy. Why does it weigh less? All right, so we've talked about this before. If you take two particles and they form a bound state, then they weigh less. The tighter they're bound, lesser they weigh. So in this heavy nucleus, when you go from here to there, each nucleon is more tightly bound. So these guys in total weigh less than this guy. Okay. So that's what's happened. Okay. All right, so that's the story. Let's do the problem now. Okay. Okay, so in nuclear fission, a nucleus splits roughly in half. What is the potential? 2 times 10 to the minus 4 meters, 14 meters from a fragment that has 46 protons. So the charge of this, so remember uranium, the atomic number of uranium is 92, splits in half, it has an atomic number of 46. Okay? So the charge of this guy is ZE, and you're finding the potential at distance r. Okay, so V is KQ divided by R, and that's equal to 9 times 10 to the 9 Newton meter square by Coulomb square. Q is Z is 46, E is 1.6 times 10 to the minus 19 coulombs, and R is 2 into 10 to the minus 14 meters. All right, so this is 10 minus 5, and 10 to the 4. Okay, so 10 to the 4 volts, 9 into 46 into 1.6 divided by 2. Okay, so let's take care of all of that. .31 into 10 to the power of 6 volts. Okay. And then they ask you, what is the potential energy in MeV of a similar charge fragment at this distance? So remember, you got two nuclei of similar charges, Q, Q. Now, the potential energy of these two charges when they split is given by K, Q1, Q2 divided by R. We just found this portion. That portion was that. So all you have to do is multiply by Q2 to get the potential energy. Okay. So the potential energy U is 3.31 million volts times that charge. And so this works out to 13 joules. Okay. Now, that won't make a whole lot of sense. Let's do it like this. What I'm going to do is convert it into electron volts. And 1 electron volt is, okay, so okay, so there's the conversion factor. All right, so here's the lure of nuclear energy. Okay. So again, what did you do? You took a large nuclei and you split it into two, and these guys split, they're both positive, and they'll fly apart. Okay. So they have potential energy, and this is what you calculated. The potential energy is 150 MeV. When you burn a molecule of carbon, so you burn carbon, you're combining it with oxygen, and you form carbon dioxide. Or burn a molecule of methane, for instance, natural gas, CH4, and you can combine that. And I'm not going to balance the equation, plus water. And then you get energy. The energy you get here is about 100 electron volts. The energy you get here is 1,000,000 times greater when you split one nuclei. Okay, and that's the lure of nuclear energy. Okay, yep.
And if you dispose of nuclear waste correctly, it is kind of better than the burning of fossil fuels, right? Like for the environment.
In my opinion, yeah.
Fusion would be the best though, right?
Yeah. It'll happen in your lifetime. All right. In a particular region, the electric potential is given by that. What is the electric field in this region? Do you guys remember how electric field and electric potentials are related? Gradient of V. Okay. So minus okay. So our function V is that, so del V by del X. Okay. So let's see. Who wants to do this partial derivative? Del V by del X. You want to do it, Sean? Hang on a second. You know why I asked you. Andrew?
I haven't taken Calc 3 yet.
You know derivatives, don't you?
I do know derivatives.
We've done partial derivatives many times here.
It's true.
Mm-hmm. All right, go ahead, try it. So just take the derivative with respect to x, treat every other variable as constant.
Negative y squared z plus 4y.
Negative y squared z plus 4y, very good. See, I mean, you already learned Calc 3.
And then it's 2y 2y x.
2x z.
Plus 4x.
Yep.
And then the last one would be, it'd be negative xy squared plus 4xy.
Okay, so there's no variable z there, and so 4xy is a constant, so it'll be 0. Okay. All right, see, that wasn't that hard. So the electric field is y squared z minus 4y I. That's the x component of the electric field, plus 2xyz minus 4xj plus xy squared k. All right? So you're still not paying attention, Sean. You're wasting your time. All right. Don't laugh. You're hurting yourself the most, and nobody cares. The surface charge density on a long straight metallic pipe is sigma. Don't look for support either. What is the electric potential outside and inside the pipe? Assume the pipe has a diameter of 2a. Okay. So you guys saw that the way potential is related to electric field, we did a line integral. Okay, so V2 minus V1 equal to minus 1 to 2 E dot ds. That's how you calculate the potential between 2 points. Okay. And the potential, this is a metallic pipe, so this is a conductor, and the electric field outside is radial, pointing radially outwards, and the electric field, if you check, the magnitude of the electric field is given by 2k lambda divided by r. This is outside for r greater than a. A is the radius of the pipe. What is lambda in this formula?
Is it wavelength?
Hmm?
Is it wavelength?
It's the linear charge density, okay? So it's the charge per unit length, okay? So here they give you the surface charge density. What does that mean? What does surface charge density mean?
Oh,
What does it mean, Brennan?
Does it mean how dense?
I didn't ask you.
Surface?
I didn't ask you. How about you? What's your name? Huh? Okay. What's surface charge density? So surface, just like it says, it's the charge per unit area. Okay? All right. So what we want to do is calculate the charge on a meter long of this wire. Okay? So we'll calculate, see the area is this circumference times the height. That'll give you the height, that will give you the area of this cylinder. Okay, the circumference times the height will give you this area. Yeah.
Are you using 1 meter just for convenience?
I'm sorry?
Are you using 1 meter for convenience?
No, that's what linear charge density tells you. That tells you the charge per meter.
Oh, so we're, okay.
Okay, then we'll do that in a second. So what we're going to do is calculate the charge 2 pi a, that's the circumference of the circle, times h, gives you the area of that thing, times sigma is the charge on height h, all that charge is that. And the linear charge density is q divided by h. Yeah. Okay. So per meter, that's the charge. Now you've expressed the linear charge density in terms of sigma, the surface charge density. Okay. All right, so what is it that, so we want to find the electric potential outside and inside the pipe. Okay. So now we're going to find the electric potential, let's say, from R1 to R2. Okay. So we're going to do that integral. V2 minus V1 equal to negative 1 to 2, R1 to R2. And we're going to go straight like that, E dot ds. Okay. So, all right, let me move this and do it right here. All right, ds we're going to move radially out, so it'll be d. That'll be dr. Yeah. So this is negative r1 to r2. Electric field is 2k lambda divided by r dr. Okay. These guys are constants. Integral, what is integral of 1 over r? Very good. There you go. So V2 minus V1 equal to negative 2k lambda log of r minus 2k lambda r2 over r1. Okay. So what we'll do is we'll make r1 equal to a. Okay. We'll set r1 equal to a, and so v minus va equal to minus 2k lambda log r so this is the potential at all points r greater than a. So outside the wire in terms of, okay, so that's the potential. Okay. Now you guys saw that in theory, in the lecture, the potential everywhere inside the metal is the same as on the surface. Okay, so whatever the potential is at r equal to a, that would be 0 in this case, and r equal to a log 1 is 0. Okay, so it would be 0 volts everywhere, and relative to that is what the potential is here. Okay, it'll, for r greater than a, this is positive, so the potential will be negative. Okay. So the potential here is negative, it's increasing, and it's 0 at this point and 0 everywhere inside. Okay. Okay, one more problem. Find the electrostatic energy of 8 equal charges, each fixed at the corner of a cube of side 2 centimeters. Okay, so 2 centimeters, and we're, oops. We are fixing charges at the, all right. So here's the problem. It's about tracking all the independent pairs. The potential energy of this setup is the potential energy of this pair plus 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 that pair, and so on. So you guys understand it's you got to be careful about keeping all the pairs together. The potential energy of a given pair of charges is Q1, Q2 divided by R. Okay. All right. We'll call this distance R. What is this distance?
It's a 90-degree angle.
Yeah. R squared plus R squared is equal to that. So root 2R. This is root 2R. Okay. What about the distance of the diagonal? That is R squared plus R squared plus R squared root 3R. So R root 3. Okay, now we have all the relevant distances. Okay, so now it's a matter of carefully adding all the pairs together. Okay, so we'll do 1, 2, 3, 4 pairs, and at the bottom you'll have the same 4 pairs, and then on the side 1, 2, and then there, how many sides are there? 4 sides. Okay, so 4 plus 4, no, 1, 2, 3, 4, plus 4. 12 of those guys. Okay. So U is 12 times KQ square divided by R. Everybody agree? 1 pair, 2 pairs, 3 pairs, 4 pairs. 1, 2, 3, 4. And then 1, 2, 3, 4. Yeah, so 12 of those guys. Now we want to take care of these pairs. 1, 2, every face has 2, and there are 6 of those faces. A cube has 6 of those faces. So that's 12 as well. Plus 12 times KQ square divided by R root 2. Plus, we got to take care of the diagonal terms. 1, 2, 3. 3 of those diagonal terms. Did I get them all? 1, 2, 3, 4 diagonal terms. 4 times KQ square R root 3. Okay, so the total energy is KQ square R 12 plus 12 over root 2 plus 4 over root 3. Okay? So it's just a matter of counting all the pairs.